Welcome back, everyone. Ready for another deep dive? Today, we're looking up, way up. We're tackling a question I bet you've all wondered at some point, while stargazing, just how DO satellites stay up there.
It's a question that's fascinated people for, well, pretty much forever. Even now, with all we know, there's still something amazing about how these objects seem to just float up there, defying gravity.
Right. And get this. Our source material today, a physics applet and some text explaining it, mentions something super intriguing. A satellite's total energy is always, get this, negative. Sounds kind of crazy, right? How can something be full of energy zipping around Earth and yet be in a negative state?
Yeah, that definitely throws people off. It's all about perspective, though. Imagine, trying to pull a metal ball away from a really strong magnet. It takes effort. You're putting in energy to fight that magnetic pull.
Okay, I'm following.
So it's similar for a satellite. It takes energy to get it up there, to overcome Earth's gravity. That effort, so to speak, shows up as negative potential energy.
So it's not that the satellite is lacking energy, but more like we're comparing it to, like, a zero energy state, way out there, infinitely far from Earth.
Exactly. And the further out the satellite is, the less negative that potential energy becomes. Like it's getting closer to that 0 point.
That makes sense. But before we get too deep into this whole negative energy thing, let's break down the basics. Our source talks about kinetic energy and potential energy, the two kinds a satellite has.
Right. Like a car speeding down the highway or, I don't know, a spinning top. A satellite has kinetic energy because it's moving. The faster it goes, the more kinetic energy it has.
Right, so that's the energy of motion. What about potential energy then?
That's all about position. Think of like a ball you're holding high up. It's not moving yet, but it could fall, and when it does, that potential turns into kinetic. Same for a satellite. Its gravitational potential energy depends on how far it is from Earth. The further out, the greater the potential.
So as a satellite orbits, it's constantly switching between these two types.
Exactly. Closer to Earth, it speeds up, trading potential for kinetic. Further away, it slows, and that kinetic energy converts back to potential.
Like a cosmic dance. But our source also says the total energy of a stable satellite stays the same despite this back and forth. How does that work?
Picture a seesaw, right? One side goes up, the other down, but overall it's balanced. Same idea here. As kinetic energy increases, potential decreases, and vice versa. This perfect balance is what keeps the total energy constant.
Fascinating. Now, for the math lovers out there, our source gives us some equations for all this. Want to break those down a bit?
Sure. Kinetic energy is pretty straightforward. It's half the satellite's mass times its velocity squared. So heavier satellite or faster speed equals more kinetic energy.
Makes sense. What about the potential energy equation?
That one's a bit more complex. It involves the satellite's mass, Earth's mass, this universal gravitational constant, and the distance between them. But the key takeaway is, as the distance increases, potential energy gets less negative, heading towards zero at, like we said, an infinite distance.
So a satellite's total energy, adding up the kinetic and potential, is affected by all these things: mass, speed, distance. But how does this constant and always negative total energy actually matter for, like, real-world space missions?
Ah, great question. That's where things get really interesting. Because by understanding this energy stuff, we can calculate exactly how much is needed to launch a satellite into a specific orbit.
So, like, we can use these equations to figure out the energy needed to get a satellite to a certain height and speed, all perfectly planned out.
Precisely, and that accuracy is crucial for a stable orbit. It's like aiming for a bullseye, but on a cosmic scale, taking into account everything that affects the satellite's energy.
That's wild.
Yeah.
It's incredible how we can use these, well, kind of basic physics principles to do such amazing things in space. But what about when we want to go even further beyond Earth's pull?
Now that brings us to the concept of escape velocity, which is the minimum speed needed to overcome Earth's gravity and head out into deep space. It's all about exceeding a certain energy threshold. And those equations we talked about, they're key to figuring that out.
That's where this negative energy idea really clicks for me. If a satellite is always negative, it makes sense that to escape Earth, it needs to get boosted to a positive value. Like it's got to pay off its gravitational debt, right?
Exactly. And that's a whole other fascinating topic. How do we actually achieve that energy boost? And what does that mean for, say, traveling to other planets? But that's a story for another time. Getting to escape velocity, that's no easy task. You need a lot of energy, usually from those giant rocket engines we see blasting off. But there are other kind of sneakier ways to change a satellite's energy, even once it's already up there orbiting.
Oh, that's interesting. I was thinking about those huge rockets, but I guess there are ways to like fine-tune a satellite's path once it's in space.
Exactly. One way is called a gravity assist maneuver. Basically, the satellite steals a little bit of energy from a planet or moon when it flies close by.
Steals energy. How did that work?
It's like, imagine a cosmic slingshot, you know? The satellite uses the gravity of that other planet or moon to change its speed and direction.
So by planning these flybys just right, we can use gravity to give our satellites a boost, making them reach their destination using less fuel, basically.
Precisely. It shows just how well we understand these energy principles, using them to navigate across huge distances in space. We can even use these maneuvers to send spacecraft to the outer solar system, even beyond.
Wow, that's amazing. Thinking about those far-out journeys, it makes me wonder about what happens to a satellite's energy as it gets further from Earth. Our source has this graph showing how kinetic, potential, and total energy change with distance. One thing that seems weird is the satellite's kinetic energy actually goes down the further it is. Shouldn't it have more energy the further it travels?
Yeah, that's a common misunderstanding. It shows why it's so important to get how these different types of energy work together. See, as a satellite moves away from Earth, it slows down. And that means less kinetic energy. But remember, the total energy has to stay the same. That's the rule.
Right, right. So to make up for the kinetic energy going down, the potential energy must be increasing.
Exactly. And remember how we talked about potential energy becoming less negative? That's what's happening here. As the satellite goes further, its potential energy climbs closer and closer to zero, that point where Earth's gravity doesn't affect it anymore, theoretically speaking.
So it's like the satellite slowly paying off its gravitational debt as it moves away, trading kinetic energy for a smaller negative potential energy. It's pretty cool to see how these concepts play out in actual orbits.
It really is this delicate balance of energies, all governed by the laws of physics. And these ideas, they apply to way more than just satellites around Earth.
Oh, really? Like, what else?
Well, think about it. Anything orbiting something else follows these same rules. The moon around Earth, planets around the sun, even stars orbiting the center of a galaxy. Understanding energy helps us figure out how things move on a cosmic scale.
That's incredible. So this idea, satellite energy, it's like a key to understanding the whole universe, from small satellites to entire galaxies.
Exactly. It shows how everything's connected out there, all following the same basic laws. That's what makes this stuff so fascinating to explore. It's like uncovering the hidden workings of the universe.
I totally agree. Now, before we finish up this deep dive, I want to go back to something we touched on earlier. What if we could somehow make a satellite's total energy positive? What would happen then? What are the possibilities and the challenges of making that energy shift happen?
Now, that's a question that really gets the imagination going. It pushes the limits of what we know right now. It's a topic worthy of its own deep dive, wouldn't you say?
So we've talked about how a satellite needs positive total energy to really escape Earth's gravity. But what would that even look like? What would happen?
Well, imagine a satellite not stuck orbiting anymore, just flying off through space. It could become like an interstellar traveler, maybe reaching other star systems or even just drifting forever out there.
Whoa, that's kind of mind-blowing. But how can we actually make that happen? We've talked about rockets, but is there anything else, anything more futuristic maybe?
One idea that's been floating around is, well, literally using sails, solar sails, they're called. Big, reflective sheets catching the momentum of light from the sun. It's a constant push, not a big burst like a rocket, but still.
So instead of one big blast of energy, we could use sunlight, constantly pushing, to slowly speed up a satellite over time.
Exactly. Slow and steady, like the tortoise and the hare, right? But with a big enough sail and enough time, it could eventually hit escape velocity.
That's amazing.
Hmm.
It seems like there's so many ways to play with a satellite's energy, from powerful rockets to these gravity assists, to even using sunlight itself. It's incredible how we can use these ideas to explore space.
It really shows how clever humans are, finding these ways to use physics, the basic laws of the universe, to do incredible things, explore what's out there.
Absolutely. We've covered a lot of ground today, from the basics of energy, kinetic, and potential, all the way to thinking about sending things on interstellar journeys. We've seen how energy controls every move a satellite makes, and we've even imagined breaking free from Earth's pull completely.
It's been a great exploration. I hope it leaves you with a sense of wonder and makes you want to keep learning about space.
I second that. Whether you're looking up at the stars or digging into physics equations, there's always something new to discover about the universe and how we fit into it. So keep exploring, keep asking questions, and never stop learning.